Welcome back. So, this is lecture number 49 and we will be talking about today the geometric and algebraic multiplicity and similarity of matrices. So, what is the algebraic multiplicity? So, algebraic multiplicity of lambda as a root of the it is a multiplicity of lambda as a root of the characteristic equation, and the geometric multiplicity is nothing but the dimension of the eigenspace of lambda. That means, the number of linearly independent eigenvectors corresponding to an eigenvalue lambda. So, these are the two numbers which we will now use for telling about the multiplicity of this lambda, because we have seen in several examples the characteristic roots, all the eigenvalues were repeated. So, that we can now quantify with the help of this algebraic multiplicity. So, algebraic multiplicity, if for instance one root is repeated 3 times, so then its algebraic multiplicity of that particular root is 3, and the geometric multiplicity will be the dimension of the eigenspace or the number of linearly independent vectors we have corresponding to that particular eigenvalue lambda. So, with these two classification we will move further, but before that there is a note here that this geometric multiplicity is always less than or equal to the algebraic multiplicity. That is an important result which one can formally prove, but it requires little more knowledge of diagonalization, etc. So, we will not prove this result now, but we will keep in mind that this geometric multiplicity is always less than or equal to the algebraic multiplicity, meaning that, for example, one particular root, one particular eigenvalue is repeated 3 times, then the corresponding geometric multiplicity, meaning the number of linearly independent eigenvectors, cannot be more than 3, they have to be less than or equal to 3. So, first we will see with the help of many examples that what are the situations arises here. So, in this case we find the eigenvalues and the eigenvectors of this matrix A, which is given as the 6 minus 2 and 2 here, minus 2 3 1 and 2 minus 1 3. So, for this for this matrix we will compute the eigenvalue and eigenvectors. We have already computed for several matrices in the last lecture. So, we are now familiar with the computation of the eigenvalues. So, here first we need to write down the characteristic equation for this given matrix, which is the determinant of this A minus lambda I. Determinant of this matrix A minus lambda I is equal to 0, and for this matrix we can compute this determinant here. So, the determinant will be like the 6 minus lambda minus 2 2 and then minus 2 here 3 minus lambda and minus 1 2 minus 1 3 minus lambda. So, this lambda will be subtracted from the diagonal entries, and with this now we can expand this. So, here the 6 minus lambda and then we have this product minus this, then we will take this 2, then minus 2. So, with this value of this determinant here, which will be coming as when we do the factorization of this polynomial, that will be coming 2 minus lambda, lambda minus 2 and the lambda minus 8. So, I skip this portion here, because in this lecture that is not important, we have already seen for several examples in the last lecture. So, what we have this characteristic equation of this matrix here as this 2 minus lambda, lambda minus 2 and lambda minus 8 equal to 0. So, what we observe now that there are two distinct eigenvalues and one is repeated 2 times. So, that means the lambdas are the 2, 2 and 8. So, this eigenvalue 2 is repeated 2 times and this 8 is repeated 1 times, and exactly that is what we have discussed about this algebraic multiplicity. So, the algebraic multiplicity of this lambda is equal to 2, this eigenvalue 2 is because it is repeated 2 times here. So, that the algebraic multiplicity of this 2 is 2, and the algebraic multiplicity of 8, because this is repeated only once. So, here the algebraic multiplicity of this lambda is equal to 8 is 1. So, this is how the algebraic multiplicity and the geometric algebraic multiplicity is defined. To define the geometric multiplicity corresponding to lambda is equal to 2 or lambda is equal to 8, we need to get the eigenspace of these vectors of these eigenvalues. So, the eigenvector corresponding to this lambda is equal to 8. So, remember this lambda is equal to 8 was repeated once, though we have already the result that the geometric multiplicity cannot be more than 1 now in this case, because the algebraic multiplicity of this lambda is equal to 8 is 1. So, without calculation of the eigenvectors as well, we can claim that the geometric multiplicity will be 1, because definitely there will be one linearly independent eigenvector corresponding to this lambda is equal to 8. So, there cannot be 2 linearly independent eigenvectors. That result says, where we have that this algebraic multiplicity is always bigger than the geometric multiplicity. So, here we know though beforehand that there cannot be 2 linearly independent vectors, it has to be only 1, because the algebraic multiplicity of this lambda is equal to 8 is 1, and it is must to have at least one eigenvectors, because that is what the foundation says. So, we have already this a minus lambda I, and the determinant is equal to 0. So, we have non-trivial solution always for this equation here, a minus lambda x is equal to 0. So, there will be definitely one linearly independent eigenvector, but there cannot be 2. This is what we will see in this case as well. So, here this is a minus lambda I. So, this lambda means 8 here was subtracted from the diagonal entries of A, and then we have x 1, x 2, x 3, and the right hand side this 0 vector. So, we can reduce to this echelon form this matrix, and so 2 minus 2 to first row as it is, and then here we can subtract this. So, this will be 0, when we subtract will be minus 3, and this is minus 3, and here also we can add in the first step. So, this will be 0, this will be minus 3, and this will be minus 3, and then in the second step again with the help of the second column. So, in the first step what do we get? It is like minus 2, 2, and then here we have 0, and then minus 3 and minus 3. Here we get, when we add row 1 and row 3, so we will get 0, we will get minus 3 and minus 3. So, again with the help of this second row we can now get get rid of this number here minus 3, but this will also become 0 together. So, this is the situation, this is the row reduced echelon form for the system of equations for this matrix. And now we observe here that this is the pivot element, and here also we have the pivot element. So, the first 2 columns have pivot element, the third column does not have pivot element. So, that corresponds to this x 3 component of this vector, and which we can take as the free variable. So, there will be only one free variable, which was clear from there also, because the algebraic multiplicity was 1, and corresponding to that we cannot get 2 free variables. So, the number of free variables tells about the number of linearly independent eigenvectors. So, here we cannot have 2 linearly independent eigenvectors. So, we know in advance that there will be only one free variable. In this case there cannot be 2 free variables. So, this x 3 is the free variable, which we can choose again as alpha. Having that alpha, we can compute the x 1 and x 2 in terms of alpha. So, then we can write down this solution of this equation x 1, x 2, x 3. So, here this x 3 was taken as alpha, and x 2 comes to be from here the minus of x 3. So, we got this minus alpha, and from this equation number 1 we will got this 2 times, we will get this 2 times alpha, this vector here x 1. So, we have this alpha not equal to 0, and alpha belongs to this real number. We can take any real number here. So, this is for any alpha not equal to 0, these are the eigenvectors, and basically the dimension of this eigenspace is 1, or in other words we got only one linearly independent eigenvector, which we can take, for instance, this 2 minus 1 1. So, that is the only one eigenvector which is linearly independent. Any other eigenvector which we get out of taking this value alpha, but they are the dependent eigenvectors on this 2 minus 1 1. So, in this case we got only one linearly independent eigenvector, and therefore, we say that the geometric multiplicity that is the number of linearly independent eigenvectors corresponding to a given eigenvalue, here the lambda is equal to 8. So, the geometric multiplicity of this lambda is equal to 8 is 1. So, here that is the number of linearly independent eigenvectors. When we come to this eigenvalues, eigenvalue lambda is equal to 2, and remember it was repeated 2 times, meaning the algebraic multiplicity of this lambda is equal to 2 was 2. So, in this case we have the possibility that the corresponding eigenvectors, the corresponding linearly independent eigenvectors, there may be 2, I mean at most 2, but there may be 1 as well. We do not know now in advance. We have to compute them, because looking at this eigenvalue, we cannot just tell how many eigenvectors will be linearly independent corresponding to a given eigenvalue. But what we can tell now, because the multiplicity of this 2 was 2, or the algebraic multiplicity was 2, and we know that the geometric multiplicity will be less than or equal to 2. So, we know now that the number of linearly independent eigenvectors could be 1, or it could be 2 also now in this case. So, let us compute this. So, this a minus lambda I, when we subtract from this diagonal entries this number lambda. So, we get this equation, this system of linear equation, and then by reducing to this echelon form. So, indeed these two rows are the same. So, we can set one of them equal to 0 immediately, and out of this first row again, because it is half of this is again when we add to this row number 2. So, this will become 0, and similarly row number 3, if we subtract half of the row number 1, this will also become 0. So, this is here the operation we have taken, that the R 2 is nothing but R 2 plus half of R 1, and here for R 3 we have taken now the R 3 and minus the half of R 1. So, with this two operations, two elementary operations, we have got this row reduced echelon form of this system of linear equation, and then now we can identify that how many linearly independent eigenvectors we are going to have in this particular case. So, here this is the pivot element, which is minus 2 in this case, and the column number 2 does not have a pivot. Here also we do not have pivot. So, there is only one pivot, that is in the column number 1. So, here x 2 and the x 3, x 2 and x 3 will be free variables. So, they will be free variables now, free variables. So, we can assign any value to them. That means, we are going to have now two linearly independent eigenvectors, because the number of free variables decide exactly how many linearly independent eigenvectors we will get. So, in this case we will get two linearly independent eigenvectors, and that is what we write. So, here x 2 is taken alpha 1, x 3 is taken as alpha 2, and then we have computed this alpha 1 from this x 1 from this equation number 1. When we write in the vector form as this, so alpha 1 we have this half and 1 0, alpha 2 we have minus half 0 1. So, we got these two linearly independent eigenvectors. So, this one and this one can check that they are linearly independent. So, corresponding to this lambda is equal to 2, because it was repeated this 2 times, the algebraic multiplicity was 2, this algebraic multiplicity of this was 2, and we also got now the geometric multiplicity. So, the geometric multiplicity is also 2 in this case. So, we have the algebraic multiplicity 2 and as well as the geometric multiplicity 2. Geometric cannot be more than the algebraic one again, but in this case we got at least the equality. So, the geometric multiplicity of this lambda is equal to 2 is 2, because we have two linearly independent eigenvectors corresponding to this lambda is equal to 2. Okay, so this example 2, where we determine the eigenvalues and eigenvectors of this A. The matrix is given here 2 4 0 0 2 0 0 0 3, and in this case one can compute easily the eigenvalues will be the diagonal entries, because it is a lower triangular matrix, and for the triangular matrices we have all the eigenvalues sitting on the diagonals here. So, we have this 2 2 3, these are the eigenvalues, and the eigenvalues of a triangular matrix are always its diagonal elements. So, we have these eigenvalues 2 2 3. The eigenspace, now we will compute for lambda is equal to 2. Again, I mean here if we want to know the algebraic multiplicity, so it is 2 for 2 and the algebraic multiplicity of 3 is 1. So, here the eigenspace we want to compute now to get the geometric multiplicity. So, here the eigenspace, so A minus lambda I, so here 2 will be subtracted from the diagonal entry. So, we will get 0 there, 0 there, 1 there. So, this is the now the matrix A minus lambda I and x is equal to 0. So, what do we see here? We can actually just take this, we can interchange the row, and then we have this echelon form, row reduced echelon form. The 0 we can bring to the bottom if we like. So, we can easily convert to this echelon form here, and then we will see there will be two pivot elements here. So, this will be the pivot element, and this will be also the pivot element when we convert into this echelon form. And this middle one, so here the first column will have a pivot, and the third column has a pivot, and this x 2 is going to be the free variable. So, this x 2 is going to be the free variable. That means only one free variable, and we will get only one linearly independent eigenvector. And surprisingly here, that when we compute this x 3 is equal to 0, that is straight away from this equation, and from this equation we will get this x 1 is equal to 0. So, out of this we are getting x 1 is equal to 0, also x 3 is equal to 0, and this x 2 will be the free variable which we can take as alpha, and then this x 1, x 2, x 3 we can write down as alpha times 0 1 0. So, here in this case what we observe, though the algebraic multiplicity of this lambda is equal to 2 was 2, but now we got the geometric multiplicity as 1. So, not surprising, as I said before, that for given eigenvalues we cannot predict in advance that how many eigenvalue vectors will be linearly independent. So, we have to compute them. What we know from that result, that algebraic multiplicity is less than or equal to the, or the geometric multiplicity is less than or equal to the algebraic multiplicity, that the algebraic multiplicity of this 2 was 2. So, we know that there will be at most 2 linearly independent eigenvectors. There cannot be 3 linearly independent eigenvectors, for example, in this case, but we do not know whether there will be 2 or there will be 1. So, what we have observed in the previous example, though the algebraic multiplicity was 2 and the geometric multiplicity was also 2. In this case, we have the algebraic multiplicity 2, but the geometric multiplicity is just 1 in this case. So, here the geometric multiplicity is 1 because we have one linearly independent eigenvector, and the algebraic multiplicity of 2 is 2 because this 2 was repeated 2 times. Coming to the eigenspace of this lambda is equal to 3. So, we know already that there will be only one. So, in this case we know that there will be only one free variable definitely, because the algebraic multiplicity is 1. So, we cannot have more than one linearly independent eigenvector. So, here if we compute this A minus lambda I, x is equal to 0. So, we have this, and then when we solve this system, so we will observe that there are two pivots in this case. When we just we can just make this to 0, and then this will become also a pivot, because this will not be 0 in that case. So, we will have two pivot elements, and this x 3 will be the free variable in this case. So, therefore, this alpha is corresponding to x 3, and this x 2 will be 0 and x 1 will be also 0 from this structure of the matrix. So, we will get the solution alpha times 0 1 1, and as expected, there is only one linearly independent eigenvector corresponding to this lambda is equal to 3. So, the geometric multiplicity of this lambda is equal to 3 is 1, and the algebraic multiplicity of this lambda is equal to 3 was also 1 in this case. Another example where we will find the dimension of this eigenspace of this lambda is equal to this very special matrix here 1 0 0 1 1 1 1 and 0 0 1. So, in this case again we need to write the characteristic equation. So, that means a minus lambda I is equal to 0. So, 1 minus lambda here 1 minus lambda and 1 minus lambda and that determinant. So, what we will observe in this case that the characteristic equation is lambda minus 1 power 3 is equal to 0. So, we have these 3 roots. So, 1 1 1. That means this algebraic multiplicity of this lambda is equal to 1 is 3 now. So, we have an example where all these we have the same eigenvalues, but repeated 3 times. When we compute the eigenspace here, meaning we have to compute the eigenvectors. So, with this equation a minus lambda I x is equal to 0. So, what will happen in this case, that when we take this minus lambda I, so minus 1 from the diagonal entries. So, this diagonals will be also 0, and we have this very simple example, and in this case there will be only one pivot. So, this first column will have pivot and the second and the third one will be the free variables. So, this is going to be the pivot element and then nothing else. So, we have the free variable, we have the free variable. So, there are 2 free variables, meaning 2 linearly independent eigenvectors. So, here for x 2 we assign alpha 1, x 3 we assign alpha 2, and from this equation which says x 1 plus x 3 is equal to 0 means x 1 is equal to minus x 3. So, we get here x 1 is equal to minus alpha 2. So, when writing in this vector form, we have x 1, x 2, x 3 as alpha 1. So, this component here is 0. So, 0 and then the second place will be 1 and then 0. For alpha 2, at one place here minus 1 and then 0, and x 3 is all alpha 2 here. So, 1. So, we have this x 1, x 2, x 3 as alpha 1 times this 0 1 0, alpha 2 times minus 1 0 and 1. So, there are 2 linearly independent eigenvectors corresponding to this eigenvalue 3. So, eigenvalue 1 here, which was repeated 3 times. So, the algebraic multiplicity of this lambda is equal to 1 was 3, and the geometric multiplicity of this lambda is equal to 1 is 1. Oh, sorry, 2. So, there are 2 linearly independent vectors. So, the dimension of this eigenspace is 2, or the geometric multiplicity of this lambda is equal to 1 is 2 in this case. So, again, though it was repeated 3 times, but we got only this dimension as 2, not 3 and not 1, but the possible values here could be 3, it could be 2 as this is the case here, but it can be 1 as well. In this example, again we will take this identity matrix. So, very simple to evaluate. So, we have we want to find the dimension again of the eigenspace of this A is equal to this identity matrix, and if we write down its characteristic equation, we will get this lambda minus 1 power 3 is equal to 0. So, again we have these 1 1 1, the algebraic multiplicity of this eigenvalue is just 3 now. So, corresponding to this 1. So, algebraic multiplicity is 3, and if we compute the geometric multiplicity now, that is interesting. So, the eigenspace will be computed by this A minus lambda I x is equal to 0, and therefore, when we subtract from the diagonal entries this eigenvalue 1. So, what we will get this 0 matrix here, and x 1, x 2, x 3 is equal to again the 0 matrix. So, what do we see now in this case? That there is no pivot, there is no pivot here, and all the variables x 1, x 2, x 3 they are the free variables. So, we can choose, we can assign any value to x 1, x 2, x 3, they are free here, and that is very special case which we have just seen now, that we got this 0 matrix here as A minus lambda I, and then we have the possibility of choosing this x1, x2, x3 freely. So, whatever we like, and we have taken alpha 1 here, alpha 2 and there alpha 3, because all three are free variables, and then this x1, x2, x3 we can write down in terms of these alpha 1, alpha 2, alpha 3 as this combination alpha 1 this 1 0 0, alpha 2 0 1 0, and alpha 3 will be 0 0 1. So, we have 3 linearly independent eigenvector in this case corresponding to this lambda is equal to 1. So, the algebraic multiplicity of lambda 1 was 3, and also the geometric multiplicity, which is the dimension of the eigenspace, that is also 3 in this case. So, we have seen in this example that if it is repeated 3 times, it is also possible that we can get the full dimension here, the dimension of the eigenspace, that is 3. As many times as the lambda was repeated, but what that result says that it cannot be more than 3, and naturally that is the case here, because the dimension that is the full dimension, because the elements belongs to this R3, and we cannot have the dimension more than 3. In that sense also we can conclude here. There is a concept here, the similarity of matrices, which we will introduce here, and we will continue further discussion in the next lecture. So, an n cross n matrix B is called similar to an n cross n matrix A if we have this B is equal to P inverse A P. If we have this relation between the matrix A and B, then we call this B is similar to the matrix A, or A is similar to the matrix B. And what do we this P, what is the P? For some non-singular matrix P, if there exists a matrix here, this P inverse, I mean this non-singular matrix P, therefore the P inverse makes sense. So, if we have this relation between the two matrices here B and A, that P inverse A P gives the B, the other matrix, then we call that these two are similar. Why do we use the similar words? Some of the properties we will check today itself, that they share very many common properties, this B and A in terms of the eigenvalues, eigenvectors, and there are other considerations as well, which we will continue in the next lecture. So, today we will see that if B is similar to A, then the B has the same eigenvalues as A, and if x is an eigenvector of A, then this y is equal to P inverse x is the eigenvector of B corresponding to the same eigenvalue. So, meaning if we know the eigenvalues and eigenvector of one, we can get the eigenvalues, eigenvectors of the other. In fact, they have the same eigenvalues, and the eigenvector also will be just the P inverse x, where P we have introduced already in the similar T definition. So, what we take that, let us say this lambda is the eigenvalue of this matrix A, and the similar to A we have the B matrix. So, first relation we have for this A, that x is the eigenvector and lambda is the eigenvalue. So, we have this relation A x is equal to this lambda x, and what we do now, we multiply by this P inverse here. So, the right hand side we have P inverse, P is that matrix which we are talking about, this similarity there. So, we have P inverse A x, and here also P inverse. So, the lambda is constant. So, we have P inverse x there, and then what we do, we have here the lambda P inverse x the same, the P inverse A, again we have introduced this identity matrix. So, here we have introduced identity matrix, which we have written as P and P inverse x, and then what we do, this we combine here P inverse A P, P inverse A P, and then we have P inverse x. So, what do we see now, this P inverse A P, as per the definition of this similarity, that A is similar to the, or B is similar to A, that means this B we can write as P inverse A P. So, this we have this lambda P inverse x is equal to B times this is B P inverse x. So, what we observe now from this relation, that this is the eigenvector P inverse x, and this lambda is the eigenvalue of this B. So, if this B is similar to A, the B will have the same eigenvalue as A, because this lambda was the eigenvalue of A, and the eigenvector will be this P inverse x. So, we can get the eigenvector and the eigenvalue of the similar matrices if we know for 1. So, lambda is an eigenvalue of B and P inverse is the eigenvector corresponding to the eigenvalue lambda. Another result which actually we have seen already in this first result, A, B are the square similar matrices, then they have the same characteristic polynomial. So, eventually we have seen already that they have the same eigenvalues. So, if we have the same eigenvalues, meaning they have the same characteristic polynomial, but this is just another way of looking at it. So, we take this B is P inverse A P, this relation, and then if we get this determinant B minus lambda I, that is the characteristic polynomial B minus lambda I, the characteristic polynomial of this B here, is equal to the determinant, this B we will replace by this P inverse A P minus the same thing, this P inverse P, that is the identity matrix we have introduced here. I mean, you can see easily that this is nothing but the lambda I, because lambda we can take common, then we have P inverse I P, and then P inverse I is equal to nothing but the P inverse P lambda times, and this is I. So, lambda times I. So, we have again here this is nothing but the lambda times I only, but we have rewritten in this form that P inverse lambda I and P. So, here the determinant we have P inverse, let us take common from both, and then we have A here and minus this lambda I and P from this right hand side we can take as common. So, now this A minus lambda I, and then this we can use the property of this determinant here, the product of these three matrices, that means the determinant of P inverse, determinant of this middle one A minus lambda I, and the determinant of P. So, here the determinant of P inverse and determinant of P will cancel out each other, we will get just one here, and what we will get, that is the property of this determinant P and P inverse, they are just the reciprocal. And here we have determinant of A minus lambda I. So, what we have seen that the determinant of this B minus lambda I is equal to determinant of this A minus lambda I. So, they have the same characteristic polynomial. In other words, we can say again that this A and B will have the same eigenvalues, and we have seen again in the previous slide here the relation for the eigenvectors as well. Okay, coming to the conclusion. So, in this lecture we have talked about the algebraic multiplicity, and that was nothing but the number of occurrence of an eigenvalue, and we have also seen the geometric multiplicity, that was the number of linearly independent eigenvectors associated with that eigenvalue, and always this is the case that geometric multiplicity is less than equal to the algebraic multiplicity. And we have also talked about the similar matrices, that means B and A are called similar to each other, they are the similar matrices if we have this relation that B is equal to P inverse A P for some invertible matrix P. So, these are the references used to prepare these lectures, and thank you for your attention.